So folks, one thing we have to do often is give the area of a sector of a circle, and textbooks don't usually go through the derivation of this, and I'm not going to in its entirety either, but I'm going to point the way to doing the full derivation. First of all, if you're willing to assume that the area of the sector of a circle of fixed radius is proportional to the angle of that sector, then the derivation is straightforward. What do I mean by that? Well, let's say we've got this circle right here, maybe here's the center, and here is the angle pi over 4. And one way to look at that is, hey, we've maybe broken this circle up into 8 slices, and if you assume, and this is the assumption, that the area of that sector right here, the area of this slice, is proportional to the angle that we've taken out of this circle, then finding the area that is straightforward. Let's go ahead and check that. So the area of the sector is equal to some constant of proportionality times the angle of that sector. Well, in our case, for this example right here, we can go ahead and actually compute the area of the sector because it's just 1/8 of this circle's total area. So it'd be 1/8, and let's go ahead and label this. Let's say this circle has a radius of r. It'd be 1/8 the area of the circle is equal to that constant of proportionality times our angle, in this case pi over 4. And we know that the area of a circle, if we assume that formula, is pi r squared, and that needs to equal k times pi over 4. And so now we can solve for that constant of proportionality. If we solve for k by multiplying both sides by 4 and dividing both sides by pi, we end up with that k is equal to 1/2 r squared. So the area of the sector of a circle is equal to 1/2 r squared times theta, or we more often give it as 1/2 times theta, radius squared, either way. So that is the formula for the area of a sector, but the problem is we assumed this first statement here. If you ever forget the formula for the area of a sector, I would go ahead and jump into this assumption and go ahead and derive the formula that way. But actually, if we don't make this initial assumption that there's anything that says this has to be a linear proportionality relationship between the area of a circle and its angle theta, then actually computing the area of the sector is fairly tedious. So at this point, folks, if you're happy with this formula, if this argument sort of made sense to you, feel free to move on, even though it's not a true justification, it's not a true proof. But if you don't want to assume that, what could we do? Well, let's go ahead and assume we're in the first quadrant. Assume the circle's at 0, 0. And the sector is in the first quadrant. And in fact, let's go ahead and with one side on the x-axis. And although this seems like a lot of assumptions, it really isn't, because if you have a circle that's, any angle between 0 and pi over 2, you can go ahead and just reorient your axes to make that work. And if it's greater than that angle, you could go ahead and piecemeal out the formula and you would still arrive at the same result. So although it seems like a big assumption, it really isn't. So here we've got a circle, let's say of radius r, and here is the sector that we're interested in computing the area of. Let's see here. So we want to compute the area of this sector, and we're assuming that we know both the radius and that angle theta there. So the key idea, in my opinion, is to go ahead and break this up into 2 parts. So we'll call this area 1 here and area 2 here. Area 1 can just be obtained through trigonometry. So the area, so first of all, the area of the sector is equal to A1 plus A2. Let's say A1 is 1/2 times its base times its height. It's a triangle. We're assuming we have that formula. And in this case, the height of the triangle, well, the base of the triangle is 1/2 times the cosine of the angle theta, times r cosine theta, excuse me, we're not assuming this is unit, r cosine theta. And the height is r sine theta. So we get that the area of that first region is 1/2 r squared cosine theta sine theta. Now, that wasn't too bad. What becomes tedious is finding the area of region 2 there. So one way to look at that, let me give myself another axis. Let's see here. Sure, that'll work. One way to look at that is, here is that region 2, where we're just focusing on that region 2 here. This is our A2. And we want to find this area. So we could go ahead and say, well, we know that this is part of the curve x squared plus y squared equals r squared, where that's the x, where we have the x and y coordinates, because this is just some region, this is just some part of the curve of the entire circle that continues on around this. And so we could go ahead and set up an integral to find the area of that second region. And the integral formula is going to go from, let me first start out by just saying a to b, and then we'll find those. It's going to go from a to b, and then we just want the area below that curve. And if we write that as a function of the variable x, which can change as theta changes, then this would be the square root of r squared minus x squared dx. Okay. Well, what are a and b in this case? Well, a is just the same as that width of that triangle, that base, which we've already said is r cosine theta. So we've got that is r cosine theta times the integral, and then we have up there we've got b, the upper limit of integration. Well, that's just the radius, because if theta is 0, that's just the radius of the circle, so that's r. And then we've got the square root of r squared minus x squared dx. Now, this is actually not a very easy integral to solve and requires a trig substitution. And to make that work out nicely, a lot of the assumptions rely on the fact that I assumed we were in the first quadrant. So at this point, I'm going to cheat and just go ahead and give you the result of this integral. It's a fairly tedious one to compute, but you can do it using trig substitutions from your Calc 2 knowledge, and you can do it without reverting to polar coordinates, which we need to do if we're trying to come up with a formula for our polar coordinates integrals. So at this point, I'm asking you to take on faith that this integral eventually, with all of our assumptions, will simplify to 1/2 r squared theta minus 1/2 times r squared sine, let's write cosine theta sine theta. And again, you'll need to justify that if you're looking to do a formal proof. But at this point, we've got A1 and A2, and we said that the area of the sector, which was equal to A1 plus A2, that would be 1/2 r squared cosine theta sine theta plus 1/2 r squared theta minus 1/2 r squared cosine theta sine theta. And that just simplifies to the area formula for the sector of a circle, which we all know as 1/2 r squared theta. So there's a quick, not complete because of this part right here, but there's a quick justification for that without making the original assumption that the area of a sector is proportional to the angle of that sector. Regardless, though, we end up with the correct formula. I hope this was helpful, folks. Thank you very much.